So to summarize everything we've learned about hypothesis tests, you have what's called the null hypothesis. And we have this nice notation of an H with a little 0 on it. And that's the statement being tested. Usually this statement represents your status quo, and our goal is to assess the strength of the evidence against the null hypothesis. And your null hypothesis is not rejected unless there's convincing evidence from the sample data that it's false. So that's kind of an important thing there. And we'll usually think of the null hypothesis as what we kind of want to disprove. So then our alternative hypothesis, which we'll do an H with an A, is a statement that we'll accept if we decide the null hypothesis is false. Sometimes it's called the research hypothesis because it's usually what you're actually interested in proving. So if you think about it, people aren't usually going to be interested in proving like a die is fair. They'd probably be more interested in being like, oh, that die right there is not fair. It's the more interesting thing usually. The hypotheses will always refer to our population parameters, and there are different kinds of alternative hypotheses. So because we've been doing a lot of talking about our population mean, we did confidence intervals for population mean, it makes sense we're going to do hypothesis testing for population means. Now if you have a null hypothesis that your mean is equal to say 3, then there's 3 different alternative hypotheses you could do. The first 2 are alternative or one-sided. Okay? You could think that either the mu is 3 or that mean is 3, or that my mean is greater than 3. Or you might think that the mean is less than 3, or you might think that the mean is just not equal to 3. Most of the time we'll be interested in doing a one-sided. So this would be based on your research. You would want to show that, say, like the weight loss was at least 3 pounds, or that, I don't know, maybe the weight gain was less than 3 pounds, just depending on what you're talking about. Okay. You, as the researcher, will either be interested in showing that your mean is greater than a specific value, less than a specific value, or just not equal to a specific value. Now, sometimes people like to look at the data and then write the alternative hypothesis or pick their significance level. Ethically speaking, you're supposed to pick your hypotheses. You're supposed to kind of know in advance what you're trying to prove, and you also pick the significance level before you actually look at your data. And let's see, our test statistic, remember, is some number or value that you compute from your data, and your test statistic helps us find evidence against the null hypothesis. Okay, let's actually cross that off, the for or against the null hypothesis, because we're always looking for evidence against the null hypothesis. So we use the test statistics because we don't just want to report all of the raw data to our boss. We kind of want to boil it all down into like one number we can give him. For most hypothesis tests, we're going to base our test on a statistic that we use to estimate the unknown population parameter. Okay, and if our null is true, we'd expect our estimate to be very close to the value of the parameter in the null hypothesis. So if we get an estimate that's very different from our hypothesized value, we'd have evidence against the null. And to see how far the estimate is from the parameter, we're going to standardize it. So for a bunch of tests we do, we're going to standardize, and it'll always be your estimate minus your hypothesized value over standard deviation of the estimate. So if we are talking about means, we would use x bar to estimate mu, right? And so if our null hypothesis is that mu equals 3, we would expect my sample mean to be close to 3. And if we're going to standardize, our estimate is x bar. Our hypothesized value would be the mean. Now notice when we write this mu here, we put a little 0 on it. The reason why is to remind you that it's the value in the null hypothesis. So in our case, our null hypothesis is 3, so it would be 3. The standard deviation of the estimate, so that means standard deviation of x bar. Your p-value, once again, is the probability of getting an outcome as extreme or more extreme than the actual observed outcome if the null is true. Now, extreme means far from what we'd expect if the null were true. which means, and this is the very important part here, the smaller the p-value, the stronger the evidence against the null hypothesis. So smaller p-values give you more evidence. And something called statistical significance. If your p-value is as small or smaller than alpha, so a small p-value means that the data is statistically significant. So make a note, this is one of the things you'll want to remember. Small p-value means statistically significant. And your significance level alpha is your amount of evidence against the null hypothesis that we require to reject the null. So if we're choosing alpha equals 0.05, we're requiring that our data is going to give such strong evidence against the null hypothesis that our data would only happen 5% or less of the time when the null is true. Okay, our common levels again are 0.1, 0.05, and 0.01. By convention, if we say it's 0.05, we're requiring strong evidence to reject the null. And at 0.01, we say very strong evidence to reject the null, and that's just what someone made up, and they're the first ones to make it up, so that's what they get to say. So this is where the chapter in your book actually starts. They just introduce a one-sample z-test for a population mean. We use the z-test when we know our population standard deviation. So we'll use this test when we want to know the value of the population mean mu, and we know the population standard deviation sigma. Now there's always assumptions for every test. Every time we do something, you're going to check, can we use this, just like the confidence intervals. And the assumptions are exactly the same. The population is normally distributed, or the sample size is large, meaning at least 30. Your null hypothesis will always be mu equals some number. So in our last example, we said mu equals 3. And your test statistic, we said that z equals x bar minus mu naught over the standard deviation of x bar. But the standard deviation of x bar is sigma over square root of n. And so instead of kind of writing that separately every time, we just kind of condensed it into one formula. So it's always going to be x bar minus the hypothesized value over sigma over the square root of n. And then based on what your alternative hypothesis is, you have different formulas for the p-values. Again, I can't say this enough. The first time I took this class, I memorized all the formulas, and I had no idea the differences between, like, the z was bigger than z, and I had to go and look every time. Then I realized you don't have to memorize the formulas or even ever look at the formulas again. Just draw a picture, okay? Because your p-value is always the area in the tail or tails, as the case may be. So coming through your different alternative hypotheses, if you have the alternative hypothesis that mu is greater than some number, so we'll say keep with our 3. If you want to know if the mean is greater than 3, then because this is a greater than, you'd be looking for high values. So you would look for the area to the right of your test statistic, z. And if you were looking for mu is less than 3, you would look for areas to the left. And if you're looking for a not equal to, then that means either side would be just as likely, so you have to look at both tails. And every time we'll just draw a little picture, and the p-value is the area in the tails. So this one would be mu is not equal to 3. So I have some steps of hypothesis testing here, and the order is pretty negotiable. They don't always have to be in this exact order. We need to specify our level of significance alpha and check our assumptions. We write our null and alternative hypotheses. Okay, and these 3 can all kind of be done in any order. But then after that, the order matters here. So we'll collect the sample data and compute the value of our test statistic. We calculate the p-value. We'll decide if we should reject or fail to reject the null hypothesis, and we reject it if we have a small p-value. And then every single time we're going to interpret our results and assess their practical importance. So just like on confidence intervals where I kind of did that interpreter every time, we'll do that again here. So a trash bag company's current bags have a mean breaking strength of up to 50 pounds. They think that their new bag will be stronger. Now, from past experience, they believe that the standard deviation of all the breaking strengths is 1.65 pounds. So that means that sigma equals 1.65. And because it's the population standard deviation, we'll use Z things instead of, say, T. Let's see. They think that their new bag will be stronger, so they want to know, their kind of question of interest is mu greater than 50. That's kind of what they're hoping to show. Let's see. They randomly select a sample of 40 new trash bags, so n equals 40. And they find a sample mean of 50.575. We want to conduct a hypothesis test, and we want alpha to be 0.05. So I kind of always go through and write down my summary information. Okay, so then we go through all of our steps. So I think we said pick a level of significance. They told me to use 0.05. You need to check your assumptions. Your assumptions say that either you have normal data or your sample size is at least 30. Okay, do we have one of those? Our sample size is 40, so we're good there on the assumptions. Now you need to write your hypotheses. I actually find it easier to write the alternative first sometimes. Remember how I said the null is the status quo and the alternative is usually what you're kind of wanting to show. So status quo would be that their breaking strength kind of didn't change. They're hoping to show that the breaking strength is stronger now and is greater than 50. So the alternative is that it's greater than 50. That's what they're hoping to show. Status quo would be that nothing changed, so it would be equal to 50. Okay, and in this class, it's always an equal sign for the null hypothesis. So we have our hypotheses. The next thing we said is collect our data and look at the test statistic. Our test statistic is easy because all we have to do is plug things in. We always use this formula, x bar minus mu naught over sigma over square root of n. So x bar is 50.575. Now mu naught is what is our hypothesized value. So you go to your null hypothesis and you say, what is the value in my null hypothesis? It is 50. Sigma is 1.65 and square root of n. Now, biggest mistakes I see people make is they reverse the order up here in the top. They do 50 minus 50.575. So make sure you put x bar first. And also order of operations, make sure you're careful here with the bottom, put it all in parentheses. So we get 2.20. And then for your p-value, what you'll do for your p-value is you come up to your alternative and you say, is this a less than, greater than, or not equal to? Okay. So for a greater than would make you think of which tail? So greater than means you should be getting high values, so you would want to go to your right. So the p-value is going to be the area in the right tail. So here's my z value of 2.20, and I just want the area to the right. Or it's the probability that z is at least 2.20. So we'll go to our normal table. We're looking for 2.20. And it looks like we're at 9.861, but that would be the area to the left, right? So this is 0.9861, so we have to do 1 minus 0.9861, which is 0.0139. So the probability that we're greater than 2.20 is 0.0139. So that is my p-value. My p-value is 0.0139. So at this point, you always have to make your decision now. So is that p-value of 0.0139? And so I always write down, I compare my p-value to alpha equals 0.05. So is 0.0139, is that bigger or smaller than alpha? At 0.0139, that would be smaller than alpha. So anytime you have a small p-value, you will reject the null hypothesis. So we'll reject the null hypothesis that mu equals 50. And my final interpretation would be that we have strong evidence that, let's see. So actually, let me come back over. So we reject the null hypothesis that mu equals 50. So that means we have evidence that my mean, the alternative, was greater than 50. So now we have evidence that our mean is greater than 50. So now let's put that in words down here. So we have strong evidence that the average breaking strength of all the bags, make sure you put all so I know it's for the population, is greater than 50 pounds. So because we rejected our null, the mu equals 50, that means we now have evidence for the alternative. So we have evidence that my mean is greater than 50. Now notice here that our point estimate of mu, or our sample mean of 50.575, indicates that mu is probably not much larger than 50. So we said we do have strong evidence that it's greater than 50, but how much greater is it? It went from 50 to 50.575. Is that going to make a difference to you as a consumer? Okay. No, you probably don't care that it's half a pound greater, right? And so here we learned that statistical significance doesn't always mean the same thing as practical significance. So one of the things we're kind of stressing is making sure you can interpret studies and actually see what they're doing. Because someone might say, oh look, I did my statistical test, I got a really small p-value, but you might say, wait, that doesn't actually make a difference to me. Okay, it's not really practically significant. So let's make a note for ourselves here. Okay, that statistical significance means that we have evidence that the mu is greater than 50. Okay. Practical significance is, would it really matter in real life? So for example, when I was doing my doctorate, my dissertation was on, I did a different teaching method and we went to check and see if does this make a difference. Now, I might say, okay, sure, it made a difference, okay, but would it be a big difference if everyone's test scores went up 20%? Like, yeah, that would be great and that would be fantastic and be worth it. But what if I did all this extra work and their test scores went up by 1%? Does that really make a big difference? No. So statistics don't, like when I plug something in my computer doesn't know if that makes a practical difference. All it checks is the statistics. So it will say, oh, sure, you have evidence that your mean increased. But it's not actually going to tell you if that's going to be practically significant. That's what humans are for. So let's try again. We want to see if a new billing system can reduce the mean bill payment time to get to less than 19.5 days. We know that the population standard deviation is 4.2 days. So let's kind of write down what we've seen so far. So we want to know, is my mean less than 19.5? We know that my population standard deviation is 4.2. We take a sample of 65 invoices, n equals 65, and get a sample mean of x bar equals 18.1077. Okay, and the final thing is, what are you going to report to your boss? Don't forget to interpret the p-value as well. So going through, notice they didn't actually choose an alpha for you, did they? Okay. So I am going to choose alpha equals 0.01. Not because there's anything in this problem that tells me to. I have full control over what I pick just so that you can see a different alpha. Okay, then we need to check our assumptions. The assumptions say, is it normal or is n at least 30? Now someone told me I should change this to calling it requirements. These are kind of the requirements to use your test. Let's see, n is 65, so that's at least 30, so we're good there. We can use this test. Then we need our hypotheses, so let's write down our null, the null hypothesis, and also our alternative hypothesis. So I like to write the alternative first. You don't have to, but it's easier for me. So we're hoping to show that our mean is less than 19.5. So mu is less than 19.5, which means what does the null have to be? The null always has to be the equals. So it would be my mu equals 19.5. Then for a test statistic, this is the plug and chug part. Z is equal to x bar minus your hypothesized mean over sigma over square root of n. So x bar is 18.1077. Mu naught, okay, this is the value in the null hypothesis. That's why it has the little 0 to remind you it matches the null hypothesis. So 19.5. Let's see, sigma is 4.2 and square root of 65. So negative 2.67. For your p-value, let's see. This is a less than alternative hypothesis. So less than means what kind of values are you going to be looking for? Things in the left or things in the right? For a less than, if I'm getting small numbers, that will make me think that it's a less than. So I would be looking for things to the left. So we'll look for the area in the left tail. So left tail because it's a less than. Okay, so z equals negative 2.67, and I just want the area to the left. So probability that z is less than negative 2.67. Negative 2.67. Looks like we're at 0.0038. So 0.0038. So that's my p-value. And now we have to kind of make our decision. So my p-value of 0.0038 is blank compared to alpha equals 0.01. Okay, so how does that compare? Is my p-value big or small? 0.038 is smaller than 0.01. So when you have a small p-value, you will reject the null. And if you reject the null, that means we have evidence for the alternative. So the alternative is that mu is less than 19.5. So evidence that mu is less than 19.5. And so my final conclusion and interpretation would be that we have very strong evidence, and I'll tell you why I wrote very strong in a minute. Very strong evidence that the average, so population mean means average billing time for all, so make sure you have the words like average and all or population mean, for all invoices or accounts is less than 19.5 days. Notice we don't actually say what we think it is, just that we're saying we have evidence that it's less than 19.5. So again, to interpret your p-value, it's if the null is true, what's the chance of getting your data or something more extreme? So if the average really is 19.5, there's a 0.0038 chance of getting a sample mean of 18.1077 or less. So because I did get the sample mean, it makes me think, okay, my average probably isn't really 19.5 because that was a really small chance, right? So continuing our example, we wanted to see if our new billing system would reduce the mean payment time. So we had our null and alternative hypotheses. So I want you to think about what values of sample means would give us small p-values and kind of which ones would give us big p-values. So if you look at this picture, I did this one. So our null is that our mean is like 19.5. And if I get things close to 19.5, so like if I get a 19.19 or like a 19.3 or like 19.6, those values are all pretty close to my mean. And those should all be fairly likely to get, right? Okay, and so these would kind of give me bigger p-values. But if your true mean is really 19.5, are you likely to get a sample mean of 10? No. Are you likely to get a sample mean of 2? Definitely not. So over here you'd have small p-values. So as you kind of move out and towards the tails, you're going to have more and more evidence against the null hypothesis that our mean is 19.5. And the more evidence you have against the null hypothesis, then that means more evidence for the alternative hypothesis. And again, as you move out this way, you're going to get smaller and smaller p-values. So the thing you need to memorize here is that the smaller the p-value, the more evidence you have against the null hypothesis. Now, as far as interpreting the weight, so statisticians, again, this is just the first person to do it, gets to make up the terminology here. So they said if the p-value for testing your null hypothesis is less than, so if your p-value is less than 0.1, we'll say we have some evidence for the null hypothesis. Less than 0.05, we'll say we have strong evidence for the null. 0.01 is very strong, and 0.001 is extremely strong. So those are the different things that you'll see me say.